Please acknowledge the next talk by Dr. Paul Ratnasamy is by the Google Meet. He is not present here. It's my sincere pleasure to welcome Dr. Paul Ratnasamy, a renowned chemist who has held leading roles in research and administration at NCL Pune and the University of Louisville, Kentucky. He is recognized for his pioneering work in zeolite chemistry and catalysis, holding over 100 patents and publishing more than 200 research papers. His contributions have been awarded with major honors, including the Padma Shri, Bhatnagar Award, and Petrotech Lifetime Achievement Award.
Okay, thank you very much for asking me to talk in an event to honor Raja Riksha. It's an honor and a privilege. In planning the talk, I was wondering what area will Raja work if we take. So I chose this area, catalysis for sustainable development, challenges in capture and use of CO2. Is it alright?
Yes, sir.
Hello?
Yes, sir.
Okay. Next slide. Can you put the next slide? Okay. This slide gives current commercial uses of carbon dioxide. So there are 4 major uses already. Urea is probably the largest use of carbon dioxide, but others are also important. Carbonate, polycarbonate. But the challenge today, the catalysis chemists and engineers, at present the fuels and chemicals are made from fossils, coal, oil and gas, which are very bad for the environment and disturb the weather pattern. Either we have excess rain or excess desertification. So can we shift the carbon dioxide and the solar hydrogen as sustainable feedstock? But both solar hydrogen is a sustainable feedstock and carbon dioxide is a waste material. What are the economic and technology challenges? Next slide.
Next slide. Yeah.
Yes. Next slide. You have to do. Yeah. Okay. Current. First, before we talk about using carbon dioxide, we should know how to get carbon dioxide. Here, that is capture. The current process is liquid amine process. Is using liquid. Take selective absorption of carbon dioxide, but liquid amine. Right? When you absorb the carbon dioxide at a low temperature, around 50 degrees, and dissolve it at a high temperature, around 90 to 100, 120 degrees. Higher temperature is the recycle of carbon. It's commercially proved 85 to 95% efficiency. The example of the amine, I can see only how. Okay. Amine used in water technology, in water solution. There are a lot of drawbacks with this amine absorption system. There is a high energy penalty. Because there is a lot of water in the water has got a high heat of capacity. Therefore, if you use it in a power plant to absorb carbon dioxide, 1/3 of the power generated by the power plant is used for the carbon dioxide absorption process. That is 3 to 4 megajoules per ton of carbon dioxide. It's a very high penalty. That is the cost of capex for this whole thing. $105 million per ton of carbon dioxide. But the carbon dioxide price, you cannot go more than 100, then it's not viable. So, amine stability is another factor. These amines decompose because many of these fuel gases contain material like oxygen, nitrogen, NOx, SOx and so on. Amine stability, corrosion, these are toxic materials. With the leakage of amine into the plant, this is a real problem. The emissions, these are limited by flue gas impurities and high water consumption. R&D challenges in this process is an improved solvent. A solvent which does not decompose, which has got a lower temperature of desorption of carbon dioxide, better process integration, lower temperature of solvent determination, and pre-clean the flue gas. Because the flue gas, see, in a sugar plant, sugar factory, the carbon dioxide is very pure, 99%. But if you take a coal-fired power plant, it contains so much sulfur, nitrogen, oxygen, particles, so the solvent should be able to handle it. Right now it is not. So these are the, next is the solid adsorbent. Can be absorb the carbon dioxide and then desorb it, because you have the high pressure desorption, temperature desorption. But these are not commercial. Only pilot plant demo. The efficiency is good and they are lower energy of penalty. Per ton of carbon dioxide, they are only 2 gigajoules. Whereas it is double in the case of the liquid amine. Drawbacks are, when they test in the lab with pure carbon dioxide, they perform very well. But for real flue gases, the materials in the salt, water, nitrogen oxide, they poison. So the challenge is to develop adsorbent with high CO2 capacity, CO2 absorption capacity, at low particle pressure. See, the particle pressure varies. The carbon dioxide from sugar plant is almost 98-99% pure. Whereas in a coal-fired plant, it is hardly 5% carbon dioxide. Maximum gas goes up to 15%. So the partial pressure is low. The solid should be able to be absorbed at high partial pressure, which is not difficult, as well as low partial pressure. We select low temperature regions around it, because this is where the energy comes, and tolerant to leak impurity, water, sulfur, oxygen, nitrogen. Next slide. Next slide, please.
Yes.
Okay. More challenge one. More selective and stable solid adsorbent for CO2 capture. Worldwide efforts are going on. Under development. Some of the solids adsorbent for insulin they come in 5 years. Amine functionalized hydrophobic mesoporous solid. Hydrophobic is important because most all the impurities things contain water. If you have a hydrophilic solid, the water will take priority of absorption compared to carbon dioxide. So the carbon dioxide is an acidic molecule, it is not so hydrophilic. So you look at hydrophobic adsorbent, some of these are given there. And another challenge, we can develop polymers of them, which are hydrophobic and which are absorb carbon dioxide. Water stable, fluorinated hydrophobic MOF 808. MOF is metal organic framework. These are the hot materials now. these two. The magnesium was, this is the zirconium one. And here, uh, they are better than the other zeolite or other material. But there are limitations in MOF process. Their stability is a problem. Scalability, you can make it in small quantity, kilogram quantity, but making in tonnage quantity is difficult and cost. They are more expensive than zeolite. But zeolite are poisoned by water. So, the regeneration of the material. And then for direct air capture, you really require very high capacity for absorption. So, any breakthrough would come in the soil absorption during the MOF. These are basic materials. The basic oxide will preferentially absorb carbon dioxide because carbon dioxide is an acidic molecule. That is why in magnesium, because these are basic solids which will preferentially absorb carbon dioxide. The carbon nanotube have been tried. They are more tolerant, but they are very expensive. Local. In any technology, economic is front. You should never forget, keep it always in mind in developing any technology. Challenges and limitations of MOF. So then, what will be the next generation of adsorbent? It can be the MOF or it can be functionalized hydrophobic material. Next slide. Next slide, please.
Yes, yes.
Yeah, I don't see it.
We are on the next slide.
Challenge to generate syngas from carbon dioxide and hydrogen. Syngas is a general platform. If you can make syngas from carbon dioxide from waste and electrolytic or sustainable hydrogen, you can make any fuel, organic hydrocarbons gas. For that, use the reverse water gas shift. Lot of research has been done on water gas shift, but not so much has been done on the reverse reaction. That carbon dioxide plus hydrogen, it is CO next to. This is an endothermic reaction. High temperature favors CO and suppresses methanation, but increase energy input and catalyst deactivation. Catalyst deactivation occurs by two pathways. One is the metal crystallite sinteride, other is the coke. See, CO is favored by high temperature. Methanation at low temperature, methanation is more favored. So you have to strike a balance. Aging, coking, metal sintering is all higher at high temperature, where you have high selectivity for carbon monoxide. So it's a question of balancing between different parameters. That is used for the reverse water gas shift. Iron, copper, nickel are supported on alumina, cilia, cornea, small particle crystallite, constant ability of O2 minus nickel. See, the oxygen vacancy, their concentration, their mobility are very important in any syngas or reaction involving CO or CO2. Because when you convert CO2 to CO, you transfer one oxygen to the surface from CO2. So, since oxygen is magnetic, it can go in oxygen vacancies or solid. Since you are adding a negative charge, you have to reduce the cation charge. So, cerium 3 plus, cerium 4 plus goes to cerium 3 plus. This ability of a metal cation to shunt between two different oxidation states is critical in designing catalysts for reverse water gas shift. Alloy regarding the metal, allowing the nickel or other stabilize the metal dispersion. See, there are two components. One is the metal, other is the support. The role of the support is to absorb carbon dioxide, retain one oxygen, because in the oxygen vacancy, CO2 go, and then CO comes. The hydrogen plays a role in the strength of the metal between different oxidation states. And also supplying hydrogen to oxygen. Because the O2 minus vacancies go to the H plus hydroxyl group. Hydroxyl group combine to give water. So both the support and the metal are critical. And you can change the H2 to CO2 ratio. No values favor CO production, but increase synthesis and coating. Because no H2, because you beneficial role H2 and all. Too high values, if you have high H2 to CO2 ratio, you produce methane, not the CO. And there is another reaction which comes into play here at low H2 ratio. That is the reverse boudoir reaction. Boudoir reaction is a disproportionation of two carbon monoxide to carbon and CO2. The challenge is to produce better catalyst for RWGS and the reverse boudoir. Okay? Next slide, please.
Yes, sir.
Third challenge is biogas to syngas. Because biogas occurs in every industry of the sugar industry, you have a large biogas production. And municipal biogas plants where they take the sewage. So if we can use the biogas to syngas, because at present the usage is carbon dioxide is removed and methane alone is stored as compressed natural gas. So you use 50% of the carbon. If you can convert methane and carbon dioxide to syngas, 100% utilization of the carbon is coming. So there are two, three processes. One is a bio impurities for any for the reforming, you have to remove the impurities for adoption. Because metal catalysts are used, and all metal catalysts are poisoned by sulfur, ammonia, or carbon. So dry reforming is methane plus carbon dioxide, you 2CO, 2H2. The highly endothermic reaction, catalysts are nickel based, nickel alumina, nickel CDR zirconia. NCL was operated 25 years ago, a nickel CDR zirconia for 1000 hours, such a Narayana. So these are good catalysts. But still, we need improvement when we change go to very high temperature, prevent sintering. And product H2CO is 1, is good for FT. You can improve the catalyst by adding steam. The steam reforming is a standard process. We add steam to CO2, you can vary the hydrogen CO2 ratio. That is a nickel based, cobalt, copper iron on serial zirconia. If they produce less coke, because the steam burns away the coke. Dry reforming, we add oxygen to burn away the coke. And also partial oxidation of methane to CO. But that is difficult to control. So these catalysts are used, and the challenge there is separate catalyst deactivation due to coking and metal sintering. Next slide.
Yes, sir.
Methanol to aviation fuel. See, methanol to gasoline is a well-known problem. But can we go to aviation fuel? DSM-5 does not use aviation grade hydrocarbon. No, aviation grade is a kerosene basically, kerosene body weight, 150 to 220 centigrade. Carbon number wise, length carbon is 50. These are the jet train, and there are specification. So what they require is methanol to olefins. That Mobile are published patented Sapper 34 for C2C4 olefins. One drawback of that thing is ethylene is low. Probably butane is high. Once you have olefin, you have to oligomerize it to jet rate. The jet will get methanol to olefin is up to C5, C6. You want to go to C12, C15, C16. So you have to oligomerize it. And then after you oligomerize, these are NCL was using electropolyacid and acetic alumina. But zeolites are also used. The electropolyacid have advantages of beers. Zeolites for some beers. And the step 3, hydroisomerization of polymer. When you have linear olefins, the aviation fuel has a branched hydrocarbon. See the specification, flash point 38 degrees minimum, freezing point minus 47. See, if you have all linear paraffin, the freezing point specification cannot be satisfied. Therefore, we have to isomerize it. Isomerizing, NCL was using electropolyacid, originally Mobile is a zeolite. After branch isomerization, you have to hydrogenate or nickel, cobalt, beryllium. And you have to control the aromatic, because the aromatics affect the smoke point. The higher the smoke point, less the aromatic. Final boiling point has to be 300 degrees maximum. These are the specifications. Lancer jet has a process for making ethanol to from carbon monoxide. Now they have, we will discuss it a bit later, they have taken the steel plant. It's a biological process which takes carbon monoxide and then converts it into ethanol. It cannot take CO2. Therefore, it takes only those effluent which contain carbon monoxide or you have to add hydrogen. That's one the sugar plant output. Pure CO2 cannot be handled by nitrogen. But steel plant output, some of the cement plant output, they contain, steel plant output for example, contain 50% of carbon monoxide, 25% carbon dioxide, and another 20-25% nitrogen. So it is very good for by the lancer jet. Next slide please.
Yes, sir.
Okay. This is carbon dioxide and hydrogen. They are directly to dimethyl. The reaction is there. DME has got a high heat number. And it can be blended with the diesel up to 20%. These are the cleaner, fuel and carrier hydrogen. So if you can save 20% on the gasoline by using methanol or ethanol and save another 20% from diesel by using DME, this is very 40% saving of crude oil import. So, but methanol to DME is not economically viable in India because 70% of the cost of methanol is the methanol price. In India, the methanol is a natural gas price. Sorry. In India, the natural gas price is minimum $6 per 100 BTU. In the Middle East and Iran, they hardly $1 to $2 every day. So there is no way that a methanol made from $6 or $8 can compete with the methanol based on $2. Therefore, but we can do that directly. Can we take Singara and make DME directly? This is a reaction. CO2 plus CO H2 remove water gas shift. So again, see, in all the carbon dioxide usage, the reverse water gas shift and selective FT are the two most important reactions, family of reactions. Very functional charges, 2040 was composting coffee. Advantage, give you a higher volumetric energy density, easier to transport than methanol, higher syngas conversion since dehydration puts equilibrium forward to comparable output. So this conversion of carbon dioxide to syngas is a very important process even for this. Next please.
Yes, sir.
Okay. Okay. We use the two categories of hydrocarbons which are made from crude oil. One are fuels like LPG, gasoline, diesel, aviation turbine fuel, will come to that later. And petrochemical, olefin, propylene, butane. So if you are going to remove crude oil, how are you going to produce olefin? There are three, four routes. One is of course the carbon electrochemical route. That is CO2 plus water, electron in ethylene. This is electrocatalysis copper copper oxide. But the problem with this electrochemical route, you cannot scale it up easily. You can make few kilograms, maybe few tons. But remember, if you are going to make fuel, like the smallest amount of fuel is aviation turbine fuel. You know the amount? 9 million tons. India country. You cannot make millions of tons of fuel by electrochemical route. It's unfair. And engineering complexity are unknown. This is scaled up to 1 billion ton and more. Catalyst again, the reverse water gas shift, same thing. CO2 to methanol, there is already pilot plant in Bangalore. Here has a 200 liters per day pilot plant with CO2 to methanol. And then olefins, and then methanol to olefins. See, for the first step, to make methanol, coupled in Kalina, that we know. And for methanol to olefin, you require SAPO catalyst, SAPO 34. And these are the conditions. MTO is 30 to 50% ethylene. You can have both. And there is an Italian company, I think, NAM project. In the 70s, they had a catalyst to make short chain alcohol from syngas, to make ethanol, propanol, butanol, and those catalysts are this one. Because at that time, the mid-70s, all men was shooting out. So, reaction to syngas became very popular. But then the scenario changed and the interest dropped. Now, we can improve the selectivity for ethanol from CO2. We can make ethylene from syngas selectively. That's a fantastic petrochemical breakthrough. Next slide.
Yes.
Yeah. Challenges in electrochemical CO2 production. The electrolyzer potential for CO2 now is about 4 volt. We want to reduce it to this value because this is the value for water. Water electrolyzer, the potential electrolyzer potential is 1.1 that. At that value, it becomes more attractive. But at present, there are about 3 and 4. Increased stability of electrolyzer, there are hardly 5,000, 6,000 hours. That increases to 60,000. Increased solubility of CO2 in liquid electrolyte. This is not a problem water electrolysis. But when you go to CO2 electrolysis, so the solubility of CO2 in aqueous electrolyte, especially at temperatures like 18, 90, becomes problematic. Reduce the capital and operational expense, product separation, surplus the issue of putting on the electrolyzer. Their efficiency to low to water electrolysis. So that's the next challenge. Hello.
Hello.
Yeah, next slide.
Yes.
Yeah, okay. See, this compares producing C2C4 alcohol from CO2. There are two rules in the world global industry. One is the Lanzatic gas fermentation. Other is the typical conventional Fischer process of the world. Feedstock here, CO-rich gases, steel and coke. If you are going to use CO2, you are reducing it either to the CO and H2 or H2. This is a very important distinction. You can't use Lanzatic for all the feedstock. The feedstock has to contain a reducing reagent which can reduce the microbe or bacteria. Syngas is a typical. Next is active agent here is the bacteria. Here of course the catalyst, radium, manganese. Temperatures are low, high. Gas cleaner, both require gas cleaner. Product, here mainly ethanol. But you also have acetate and glycerin. Mixed alcohol, ethanol. Pros and cons. See the product in the Lanzatic concentration of ethanol is about 2 to 3%. Because above that, the organism is poisoned by the ethanol. So, distillation cost, concentration cost, the 3% to 100% is significant. Next slide.
Yes. Yes.
Yeah, driving time. Challenge A, cost of electronic, reduce cost of electronic. See, there are two factors which determine the cost of electrolytic hydrogen. So at present, hydrogen is made by steam methane reforming. The cost of that hydrogen is $1 to $2 per kilogram. When you make with electrolytic, the current cost is about $4. So as long as the electrolytic hydrogen cost is more than double, the steam methane reforming cost, people are not going to take advantage. The electricity cost and the electrolyzer capex is more than 70% of the total capex. You see here, electricity cost and capex cost. Proton exchange PIM also has a high capex because they contain platinum and uranium. Nuclear assembly, okay. One is raise the capacity. If electricity is raised from the solar or wind, it's not a continuous generation of electricity. If it's solar, for almost 10 to 12 hours, there is no solar electricity. So you have to require storage factor or alternate wind. But at night, wind can take up. System efficiency. The efficiency is defined as the kilowatt hour needed per kilogram of hydrogen. For 1 ton of hydrogen, 10 gigawatts of electrolyzer capacity is needed for 1 ton. Efficiency, alkalizers are 43, temperature, current density, electrolyte increase efficiency. These are the ways you can So current cost of hydrogen for alkaline and spent is 4.2. Solid oxide electrolyte 4.7 dollar per kg. What is it? For steam reforming is 1 to 2. Next.
Yes.
Yeah. See, this again compare the relative advantages and disadvantages of alkaline. We discussed about it before. Well established technology. Almost all the commercial plants in the world are alkaline electrolyzer. Then we got promise that yes, you have to reduce the cost of electricity, you have to reduce the capex cost before. These are low current, these are the disadvantages of alkaline yes. Next.
Yes.
We have seen some of them. Oh, I hope I can finish in half an hour. Summary and conclusion. Many sustainable routes are there for CO2 to useful fuel, especially ATM, because for road transport or personal space, you can put battery. You can't put a battery in an aeroplane. The weight is too much. You have to have a liquid fuel with energy density equal to at least the current ATM. It's not easy to find. Because if the surface transport, you don't need like extra battery technology is there. So, you need ATM, chemical method. For these things also, you require carbon compound, petrochemicals, chemical, polymer. All the polymers are carbon materials. To make polymers, you need monomer, olefin, and that comes from methanol or DNA. Sources for carbon dioxide. Power plant is 15%, biogas plant 50% carbon dioxide, sugar factories more than 98%. See, they have got a very pure CO2. Municipal sewage 50%, steel, cement, fertilizer, they are all there. Sources of hydrogen, solar electrolysis, steam methane reforming, methane cracking to carbon and hydrogen. But it does not have much commercial potential. The large capacity cannot be done. Technology improvements in RWTS, Fischer-Tropsch, in electrolysis, capex efficiency, carbon capture needed. For blue hydrogen, cost of electricity and capex of electrolyzer are pivotal. Cost of hydrogen reduction for steam methane reforming 1 to 2, but others is clear. I would like to explore another pathway. Suppose you take a steam methane reformer. The reformer outlet will pass through the vertical shift, so you get CO2 and hydrogen. The CO2 is fairly close. Take that CO2, absorb it in carbon capture, and then make either fuel or preferably chemicals. Somebody has estimated it. That comes to that steam methane reforming plus carbon capture. The hydrogen equal to $2.3 per kg. This is for an assumption, natural gas price at $6 MMBTU, 90% carbon capture, medium size plant. So this is I think there's one more slide, last. Yeah, this is again comparison of pressurized and fed electrolyzer. We have talked about many of them, but this is the implemented in industrial scale. Only a reason beginning to scale up before. Capex is low for alkaline because here the electrodes are nickel. There the electrodes are platinum beryllium. I think I have already experienced that. Next slide, thank you. Thank you very much.
Thank you so much, sir. I would like to inform that the next session is also going to be online. With immense pleasure, I invite our next distinguished speaker, Professor Balachandra Bange, Vice Chancellor of the Maharaja Sayaji Rao University of Vadodara. Professor Bange is an internationally acclaimed expert in catalysis and green chemistry with over 2 decades of exemplary service at the Institute of Chemical Technology, Mumbai, where he also served as a head of the Department of Chemistry. His pioneering research centers on the sustainable catalytic processes and small molecule activation, including CO and CO transformations. A prolific researcher and patent holder, Professor Bange has been consistently recognized among the top 2% of scientists worldwide by Stanford University. Please join me in warmly welcoming Professor Bange.
So, good afternoon to all of you, and today it's a privilege to give presentation on biomass to value-added products. This is on the occasion of 75th birth anniversary of late Professor R.A. Rajadeksha, who is a professor and former head Department of Chemistry and Professor of Chemical Engineering at Delhi UDCT. So let me begin with our area of interest. We are working in the area of homogeneous catalysis, then preparation and characterization of organomechanic compounds, coupling reactions, CO2 utilization, mainly activation of small molecules like COH2 to value-added products. And considering this, we have also worked on biomass-derived products based on our catalysis experience. Biomass platforms plays a significant role because when you look for the biomass production in nature, today 180 billion metric tons per year biomass is produced. Most of it is carbohydrates, then lignite and very small quantity of fats, proteins and carbohydrates, etc. Carbohydrates are building blocks for a diverse chemical platforms, and lignins are nature's richest resource of aromatic carbon used in polymeric adhesives and production of phenol compounds. On the other hand, fats, proteins and terpenes can be converted into polymers, lubricants and detergents. So when you consider the biomass platform molecule, this slide can summarize that in a short way, that initially they will be converted into sugars, phenols, starch, just a minute. Starch, collagen, cellulose, chitosan, natural dyes, lignin, waxes, hemicellulose. Now again this becomes some kind of platform for preparation of various applied molecules. Like it can be used as a bioadhesive, hydrophobes, films, liquid fuels, solid fuels, nanocomposite, biosurfactants, natural chillers, PVC replacement, hydrogens, chemical monomers, biosolvents and cosmetic waxes. So all specialty chemicals we can produce it from biomass. And there is one concept called chemocatalytic biorefinery. In this concept, we take lignocellulosic biomass and convert that via catalytic hydrolysis or depolymerization to cellulose and hemicellulose. Hemicellulose and cellulose can be converted to biofuels by catalytic HCO process. On the other hand, lignocellulose also can be converted to lignin, and lignin can be further chemical conversion using phenol aromatics, diabasic acids and olefins. Whereas cellulose and hemicellulose can be converted to sulfonol that will be act as a biofuels and chemicals via dehydration, or one can do the fermentation to give alcohols which leads to biofuels and chemicals. We can also convert cellulose and hemicellulose to hydrocarbon and biohydrogen. Again, it's a class of biofuel and chemicals. So, what type of chemicals and fuels which we can produce from lignocellulosic biomass? As I told you, cellulose via hydrolysis can be converted to glucose, and glucose becomes a platform for variety of C1 to C6 blocks. So, if you consider C1, you can get methane, formic acid, CO2, syngas. In case of C2, you can get ethanol, acetic acid, glycolaldehyde. C3 gives you lactic acid, glyceraldehyde, pyruvaldehyde, hydroxyacetone. C4 is malic acid and electrose. C5 gives you furfural and levulinic acid. C6 gives you sorbitol, fructose, mannitol and 5-HMS. Hemicellulose via hydrolysis gives you xylose, and xylose after hydrogenation or deoxygenation gives you gamma-vanorolactone, tetrahydrofurfural, pentanoic acid and 1-pentanol. Lignin, based on slow cleavage strategy, can give you glycols, phenols, monomers, and which can be further hydrogenated to give you alcohols and hydrocarbons. So let us consider some important molecules from this biorefinery concept. As I told you, we can get hydroxymethyl perfurol, which can be converted into various derivatives. For example, one side you have hydroxyl group, another side you have ketonic group, aldehyde group, and this can be converted to either dicarboxylic acid group, which is a kind of monomer for biopolymer, or you can convert that via hydrogenation to 2,5-dimethylfuran or as 2,5-DMF. Again, this is a very useful solvent. Or you can do the hydrogenation at the aldehydic part and you can get dihydroxy group, that is called as 2,5-DHMS, and this is also some kind of useful monomer for biopolymer. Another important molecule which we can get it from HMF is levulinic acid. And levulinic acid also one of the platform molecules which gives you many value-added products. Cellulose, as I told you how to convert it into 5-HMF. You can take cellulose through hydrolysis, you will get glycopyranose, isomerase, you will get fructopyranose, and after dehydration you will get 5-HMF. This is the way you can get the 5-HMF. And as I told you, 5-HMF, you have to do the oxidation. Oxidation is not straightforward because it will have several byproducts in between. So you need to develop selective catalysis to get the selective products. Even same case, you can do the catalytic hydrogenation of 5-HMF. Again, you will get many possible products. You can get the catalyst for each and every product based on the reaction condition and type of the catalyst which you can develop. And as I told you, 5-HMF can be converted to levulinic acid, and levulinic acid is one of the platform molecules. You can get converted that into levulinic acid esters. They have their own applications. Esters can be converted to 1,4-pentanediol, again a useful molecule for polymerization, or you can cyclize that to produce 2-methyl tetrahydrofuran, again important solvent, or levulinic acid can be cyclized to give you gamma-vanorolactone, again very important solvent. So many possibilities exist in the catalytic biorefinery. Then, as I told you, furfural can be converted to furan, THF, and then we can perform so many operations to get many other products like furanic acid, succinic acid, malic acid, malic anhydride, FA, then you can do the hydrogenation, you can get THFA, CPO, then you can get the 1,4-pentanediol, 1,2-pentanediol, 1,4-pentanediol based on the various catalytic processes. Cellulose or hemicellulose after acid hydrolysis can give you D-glucose. You can convert that into D-sorbitol or D-mannitol, or you can produce D-mannose and mannitol sugars, xylose and xylitol. So cellulose also can be converted to sugars like 6,6 platform. Succinic acid and its derivative also we can get it from fermentable sugars, and succinic acid can be used to prepare succinic acid esters, 2-methyl pyrrolidone or gamma butyllactone, 2-pyrrolidone or tetrahydrofuran or 1,4-butanediol. So you can see broad spectrum of chemicals you can prepare via chemocatalytic biorefinery based concepts. Then you can produce lactic acid to give you different lactic acid based products which are mentioned in this slide, like pyruvic acid, acetaldehyde, polylactic acid, one of the famous projects to prepare lactic acid to polylactic acid. Although commercial issues are there in all these concepts, we will discuss later stage how we can cover those issues. Then lignin, as I thought, bio-based aromatic rings. And lignin, you can play around with lignin with the help of various processes like thermolysis, pyrolysis, hydrogenation, alkali treatment, hydrolysis, enzymatic oxidation, microbial conversion to again give you many value-added products like acetylene, acetic acid, phenols, vanillin, then vanillic, ferulic, butyric acid, many more. Once you get glycol from the lignin, you can use it to prepare phenol catechol, and further it can be converted to benzene, cyclohexene or cyclohexane. As I mentioned to you, levulinic acid is one of the important platform molecule. This also can be converted into succinic acid, butanediol, acrylic acid, THF, gamma butyllactone, diphenolic acid and NPHF, which is a fuel additive. So you have seen that we can have chemocatalytic route to prepare different types of molecules. So our group has worked on these problems and developed several processes based on the biorefinery concept, and our goal is to develop solid acid-based catalysts which have redox sites, which has good porosity, morphology, and convert all these molecules. So I will take some examples which I have developed in our group or biomass-based refining concept. So first case I would like to talk is hydrogenolysis of biomass-derived 5-hydroxymethyl perfurol to produce 2,5-dimethyl Here we use ruthenium zirconia NCM41 based catalyst, and you can see that HMF is converted to DMF using this particular catalyst. And for that conversion, you need 160 50 bar and 1 hour, and the catalyst is ruthenium on zirconia. Why we took this problem? Because earlier reports use expensive catalytic system, requires high temperature, longer reaction time, lower yield, and leaching was the major issue, and they need co-catalyst. In this case, we have inexpensive catalytic system which works at low temperature, and the product 2,5-dimethylfurol is considered as important transportation fuel because of its high octane number and greater energy density and ultimate boiling point and lower oxygen content and calorific value compared to poor water solubility. So, when you want to do hydrogenation, you can see there are so many possibilities. HMF can be converted to 5-methylfurfuran or 2,5-bis-hydroxymethylfurol. Further hydrogenation gives you 5-methylfurfuryl alcohol, which is converted to DMF. You may need to over-hydrogenation to give 2,5-dimethyl tetrahydrofuran. So, the challenge here is you have to develop a catalyst which will give you selectively DMF, and no other byproducts are found. And we worked in that direction. So, ruthenium supported on zirconia NCl41 catalyst which we have developed gives you such type of properties which is highly selective to DMF. More details you can find it in the publication. Then we have taken another example in which levulinic acid is converted to pyrrolidones using reductive amination of levulinic acid. Here we need to take ruthenium metal anchored in the ionic liquid immobilized in graphene oxide based catalyst. This catalyst is specially designed so that ruthenium is closely held between the ionic liquid groups which are anchored on the graphene oxide. And you take levulinic acid and take primary amide and 15 bar of hydrogen in methanol at 130 degrees centigrade, you will get reductive amination reaction because this ketonic group will form imide with the primary amide and eventually it gets cyclized to give you pyrrolidons. So this pyrrolidons finds applications as a solvent, chelating agent, surfactants, intermediate for ink, agrochemical components. It is used in transdermal patches, fibers and pharmaceutical formulations for material industries. So this is the reaction. You take levulinic acid, react that with the benzylamine, and as I told you, the ruthenium GOIL catalyst can give you the cyclization, the reductive amination followed by the cyclization. So we screen several catalysts in this particular case, and we optimize this particular catalyst, that is ruthenium GOIL. 93% yield can be obtained at 15 bar in 5 hours at 130 degrees centigrade. You can see that number of such substances we have prepared using this particular technique, and many of them were novel compounds. We have well characterized, and you can get more details in the publication. Then, as a curiosity, what we did, we have taken the source like D-fructose, converted that into levulinic acid, and converted that into the final product in one pot. And that is possible. Only thing that we got less seed here, or you can take biomass waste, which is rice husk or corn straw. Again, you can convert levulinic acid and you can get the final product. You can separate this product and also separate the catalyst and recycle them a number of times. We have shown that this catalyst remains robust and works for several recycles for synthesis of pyrrolidons. So, using same analogy, we conducted another reaction in which we have prepared N-substituted isoimidazolines, and again same strategy. You can see another set of new molecules which we have produced from this particular biomass derived molecule. Then we have also prepared 2,5-diformylfuran using ruthenium supported catalyst which is supported on molybdenum clay. So you can take fructose and take ruthenium MMT catalyst, you can produce 2,5-diformylfuran. So here both the side formyl groups are there, and you can also do it from fructose to HMF, HMF to DFF. So both possibilities exist in this particular transformation. So again, DFF, diformylfuran, is a platform chemical which is used for precursor of furanic polymers, liquid fuels, antifungal agents, heterocyclic ligands for pharmaceuticals, fungicides, and renewable furan urea resin. So again, that is another application. If you wish to have a biomass derived formaldehyde furan resin, this is alternative furan urea resin you can prepare using this particular product. So you can also do this with direct synthesis of fructose to DFF. You can take fructose, convert that into HMF to DFF, or you can do it directly one-pot synthesis. So both ways you can have this particular product. Now we have also screened several other types of glucose for this particular conversion, and you can see that most of the glucose gives reasonably good yield for DFF. It varies, depends on the type of sugar we use, but using same strategy, you can convert that into DFF. Then the question arises whether we can find the replacement for expensive ruthenium metal. And from that direction we worked, and we found that cobalt aluminum hydroxide catalyst can give you conversion of one-pot conversion of fructose to 2,5-diformylfuran. So you can have good replacement based on the cobalt aluminum cheaper catalyst, and which is also stable, robust, and recyclable. So as I told you, DFF finds more application. Here just changing the catalyst and we can get the similar yields for the cobalt based catalyst. Then levulinic acid we have converted to GVL, that is gamma valproate, and here first time we have attempted to prepare chiral GVL, and there was no report which reports the chiral GVL from levulinic acid. So we have taken biomass waste or fructose, converted that into levulinic acid, and we have developed here homogeneous form of catalyst using transfer hydrogenation reaction with ruthenium based. This is the catalyst, and sorry, this is the gamma valproate, and you can find that chiral GVL has several applications because this is not a conventional GVL which is used as a solvent. This is having a very high value because it is a chiral in nature and it has a specific application so that it goes into the specialty products. So these are those catalysts which we have developed, and the first catalyst we found that it is a good catalyst to give you chiral GVL. And we have also screened various bases for this particular combination, and you can see that first combination was useful for this particular transformation. So here you can vary this particular R and prepare different types of GVL using this particular technique. So you can have permutations and combinations of different types of substitutions with respect to R is possible. You can see the GC. This is racemic GVL, and you can see here the GC, not another GC of chiral GVL. So you can see that here, this is the enantiomeric excess R GVL which we have produced using this particular technique. Then we have also worked on synthesis of levulinate esters using ionic liquids, which is called as MIM HSO4. This is very simple and cheaper ionic liquid. You can do the esterification of levulinic acid. By the way, levulinic acid esters with different types of alcohols have several applications in industry, and that's what we have showed in this particular publication. You can see different types of combinations we have performed, and all the combinations gives you the best yield for esterification. We have also worked on preparation of biodiesel using waste cooking oil, and that too using supercritical CO2 in the continuous mode, and you can get very good quality biodiesel using this particular technique. Besides biomass derived products, you can also work on CO2 based compounds, and our group is actively working on the CO2 based compounds. For example, here we have taken aziridines and we have prepared the cyclic urea using CO2 and ionic liquid based catalyst. Same way, ionic liquid also used for cyclic carbonate synthesis and many more catalysts also. So you can take epoxide, you get cyclic carbonate, and cyclic carbonate can be transesterified to give you dimethyl carbonate, which again you can use it for preparation of diphenyl carbonate and many more carbonate based chemistry you can develop. Or here you can take aminobenzonitrides with CO2, you can prepare such important drug intermediates using this particular technique. So lots of green chemistry we have developed. Due to the shortage of time, I will not go into more details, but lots of chemistry we have developed with respect to Faraday cycle chemistry, CO2 chemistry. For example, in this particular Faraday cycle chemistry, we could able to achieve the turnover number of 10⁷. So it is irrelevant to have separation and recycle of homogeneous catalyst once you get the turnover number in the order of 10⁷ and 8. This is a particular example where you can see the high turnovers at TOF. Many more reports. Due to the shortage of time, I will wind up my lecture. We have written one book on transformation and utilization of carbon dioxide. If you have interest in this particular area, you can refer to this. And renewable feedstock is always a challenging task for researchers because economics we have to match, environmental challenges we have to match, and there are lots of scientific opportunities in this area. So my appeal to youngsters that please contribute to this area. So I would like to thank all my fund providers like CSIR, DHT, UGC, and my collaborators. And thank you for your patience hearing to my talk. Thank you very much.
Yeah, thank you, sir. So I would like to conclude this session. Thank you for your valuable time and your knowledge.
Thank you. Thank you very much.
Thank you, sir.
Now I would like to request Dr. Shraddha Tiwari to give her vote of thanks.
Good evening to all the dignitaries of the dais and my colleagues and friends. Like all good things, our day of discussion and interactions is now coming to a concluding point. And on behalf of the Department of Chemistry, it is an honor to propose the vote of thanks. It is said that the quality of life is not determined by the number of breaths, but the number of lives you touch. And this is exactly what led to the genesis of the idea of having a one-day conference in the memory of Professor Rajadhyaksha. It was the idea of all his student community who came together and thought that we should acknowledge his contribution on the auspicious day of his 75th birth anniversary. And that is what culminated as this one-day conference in Catalysis for Sustainable Development. On behalf of all the people who are present in this auditorium, we begin by expressing our gratitude to his family, Mrs. Rupa Rajadhyaksha and Mr. Sachin Rajadhyaksha, who graced the occasion. The importance of Professor Rajadhyaksha's contribution was evident by the galaxy of stars that we had who were our speakers and who graced this event, starting right from Professor M.M. Sharma, Professor J.B. Joshi, Professor Vice Chancellor, Honorable Vice Chancellor Professor A.B. Pandit, Professor G.D. Yadav, and so on. And then we had a galaxy of speakers as well, Dr. R.V. Jasra, Professor Vivek Polshettiwar, Dr. Sharad Lande, Professor Sanjay Mahajani, Dr. Paul Ratnaswamy, and of course Professor Bhange from Department of Chemistry. Most importantly, we acknowledge that this idea could come into fruition only because of the collective effects or efforts by Catalysis Society of India and UDCT Alumni Association. But the driving force behind these two groups is actually the former students from the Department of Chemical Engineering who have been associated with Professor Rajadhyaksha since through all these decades and who still feel his contribution to their science. So I'll name a few of them, starting from Dr. M.G. Palekar, Dr. Dilip Chaudhary, Dr. Mayukh Varavdekar, Dr. Gopal Joshi, Dr. Shetekar, Dr. Rajendra Shende, and Dr. Pramod Kumbhar, and Dr. Manoj Kharkar, to name a few, and there are many more who are here and who are present in the audience. And I can summarize that we all have many other people in the audience who are friends and colleagues of Professor Rajadhyaksha. For example, Ms. Bhagwat and Dr. R.V. Chaudhary, who had shared many fond memories about him. Last but not the least, our audience, all the MSc and PhD students who were here right from the morning. Actually, if we put a nutshell of all the lectures, we get a fair idea of how catalysis will shape the industry in the next decade or 2 decades. So I am sure that the students must have benefited a lot, and but as I said, their presence is what made the event a success. And last but not the least, let me end by thanking our volunteer team who have been here since day one, right from the day the idea came into fruition. So thank you all, thank you for being here, and we wish to continue the good work which was initiated by Professor Rajadhyaksha. Thank you.
Thank you, ma'am, for the warm acknowledgement. As we come to the peroration of symposium, let me take this opportunity to gratify all those who made this day so meaningful. Thank you so much and have a great evening. Thank you. Also, I request everyone to meet outside the auditorium. We'll be having a high tea.